Hi, Calculus. It's Mrs. Jarosik. I am here with 4.1 notes. We are going to start chapter 4, which is applications of derivatives. So if you don't have your notes printed out yet, please take pause and take a minute to print those out or get your notebooks out so that you can take notes. Sections 4.1 and 4.2 lay the groundwork pretty much for the entire chapter. So they're pretty critical as far as the content in these sections to understand what's coming up beyond this. So some pretty good material in these two sections and pretty important material. Okay. All right. So here we go. First thing we're going to talk about are maximums and minimums. And you're probably saying to yourself, wait, I already know maximums and minimums. Well, you do know a lot about maximums and minimums. I will tell you that. What you learned in Algebra 2 all still holds, and we're going to add to that, okay? So the definition, lots of definitions in this first section. So the definition of an absolute max or min probably hasn't changed from what you think it is. So what I'm going to start out with is I'm going to draw, just in Algebra 2, we talk a lot about polynomials in general. We talk about quadratics quite a bit. But I would say, whoops, I wasn't supposed to erase. Oopsie. I would say that your most basic idea of an absolute max or a min came when you learned quadratics, probably. So the parabola on the left would be an example, the vertex of being an absolute max. And then the one on the right would be an example of the vertex being an absolute min, right? The absolute max or min itself is always a y value. Where it's located is always the x value. Still very important to understand those differences when you're naming a max or a min or where it's located. But I guess to even break it down more, this particular y value is the largest y value in the entire function graph, whatever you're looking at. This y value is the smallest y value on the entire graph. Nothing smaller y value, nothing larger y value, right? Okay, absolute maxes and mins. All right, so let f be defined on an interval d containing c. If f of c is greater than or equal to f of x for every x in d. Okay, so what does all this mean? This is a y value specifically at c being larger than or equal to anything else in the graph for the whole domain. Well, that means that if I drew myself a coordinate plane, this would be c, this would be f of c. It's the largest y value of all of it, okay? Same reasoning here. If I just made that a pretend x-axis, and that's c, that particular f of c is the smallest y value on the entire function, okay? So the next sentence reads, if f of c is less than or equal to f of x for every x in d, then f has an absolute min. So you've got your absolute min, you've got your absolute max. Absolute extreme value refers to either absolute maximum or absolute minimum values. So extrema is the plural for extremes, okay? So you might see the word extrema as well. You actually see it right there. So the function f of x equals x squared has different absolute extrema depending on the interval of interest. So if we make domain restrictions on our basic x squared graph, we come up with different absolute extrema, okay, depending on the restriction. So the first picture, all I did was rewrite what this said. It was really came out very small in the copy, and I apologize for that. Hard to read. So if you want to recopy your intervals, go ahead and do that. All right. So we're talking about x squared over its entire domain of negative to positive infinity. Okay, well, we know, we already talked about it actually up above. We know that all it has is an absolute minimum. And if we want to go so far as to say it has an absolute minimum, of 0 at x equals 0, to be even more specific, because the y value itself is 0 and it's located at x equals 0. There's no absolute max to this, right? Because those arrows are pointing up. Okay, so let's take y equals x squared on closed interval 0 to 2, or inclusive, right? 0 is included, 2 is included. Well, we have both. We have an absolute min and a max. So this is an absolute min of 0 at x equals 0. This is an absolute max of 4 at x equals 2. Okay. Now, it's a little bit different because now we have open on one side, closed on the other. So x squared from 0 to 2, 0 is not included, 2 is included. So let's go with 2 first. So at 2, we have an absolute max of 4. And then here, we don't have anything. We don't know what the absolute minimum would be. Because it's not 0 itself, the 0 is not included, it's not 0.00001. We don't know, because you could add about, a million more zeros before the 1, and that could be the value. You could add an infinite number of zeros before the 1, and that could be the value. We can't name the absolute minimum in this case. So there is no absolute minimum. All right, in the last example, 0 and 2 both not included. So it has no absolute max or min. As a matter of fact, it has no absolute or local. Doesn't matter. Has no max or min at all in this problem. Okay. All right, so maybe pause, label the next graph with your absolutes if you can. And I'm going to go ahead and label them right now. Looks like we have an absolute min at x equals a. I don't have the y value that goes with it, so. Oh, I know what I could say. All right. Hopefully you're thinking this yourself. Absolute min of f of a at x equals a. That's what I could say. All right, that's an A, not a 9. That's a really bad A. Here we go. Here we go. It's a little better. Not great, but better. All right, and we have no absolute max. Right here, remember, same reasoning as on the last 2 problems where we had, you don't know if it's 0.000 zeros and a 1. You don't know how small it actually gets. And then for this one, we don't know how large it's going to get. Like, even if we said that this was like at 4, where the 0, where the hole is, it could be 3 point and a million nines, right? We have no idea. We cannot name it. So no absolute. Okay. All right. There is no guarantee that there is an absolute max or min unless the extreme value theorem basically applies. Okay. So EVT, your next value theorem, IVT. This is EVT. So you won't have to name this theorem. You need to understand and apply the theorem. So like in IVT, when you use its own definition, when you're explaining, you don't really do that with EVT. You're really just using the process of finding an absolute max or min. EVT, as long as all of the conditions hold, you're guaranteed an absolute max or min. So we have the definition. So a function that is continuous on a closed interval, a to b, has an absolute max value and an absolute min value on that interval. Guaranteed. Guaranteed. As long as you have those two conditions, continuous closed interval A to B. So if you try to draw a continuous function A to B that doesn't have an absolute max or min, it'd be pretty hard to do. Right, so if I did even this, and I really just sort of went right beyond my B where I have it. Okay, so this is the absolute max, and it looks like this dips a little bit below that, so this would actually be the absolute min. Okay, even if this point and this point were equivalent as far as the y value is concerned, they would both be absolute mins. It's fine, it can be shared. Okay. All right, critical point. Super important what we're getting into now. So critical points will take us into all of chapter 4. You'll be using it throughout the chapter. What is a critical point? First of all, it's an x value. It's very important. It's an interior point C of the domain of F at which F prime at C is equal to 0 or F prime at C fails to exist. Is called a critical point of F. So basically what you're talking about is this first one kind of makes sense, because if you think of a critical point at which F prime is equal to 0, what do you tend to have at those locations? You tend to have your maxes and your mins, right? Your tangent line would have to be slope of 0 for a max or min to even occur there. But sometimes if your derivative is equal to 0, sometimes you don't end up having a max or a min. And if F prime of C fails to exist, so meaning your derivative is undefined there, like a corner or a cusp, it can still be a max or a min. So an absolute value graph, for instance, right? It has an absolute min, you just can't take its derivative there. So the derivative would be undefined there, but it's an absolute min. Excuse me. Wow, got two things happening here. It's an absolute min, but F prime is undefined, right? Corner or cusp situation, okay? Potential existence of a local max or min. So the critical points help us determine whether or not we have a max or a min. We're going to use them to help us determine that. So I'm going to actually add something here. So the x value where derivative equals 0 or is undefined. So critical point, super important. So your local extreme point theorem, if F has a local min or max at C, then F prime at C exists, and then F prime at C is equal to 0. I basically said that in the last, in the definition of critical point. If you end up having a max or a min, like this, okay, and the derivative exists, like you can take the derivative, right? In this example, I have an absolute min, right? In this example, I have an absolute min, but I cannot take the derivative, F prime undefined. Here, I can take the derivative. Here, I can take the derivative, okay? All right, local max and min value. Suppose I is an interval on which F is defined. C is an interior point of I. If F of C is greater than or equal to F of X for all X in some open interval containing C, then F of C is a local maximum value of F. If F of C is less than or equal to for all X in some open interval containing C, then F of C is a local min value of F. All right, let's draw one last picture that hopefully sums that up. So on the picture, I have a local max, obviously not absolute because we've got that going on. We have a local min, right? Only because we have that going on. So in the vicinity of, so on some open interval, so your f of c, which would be either this, right, or this as a separate point, is this one is higher than anything in the vicinity. This is lower or the lowest in the vicinity of things relative to it, meaning things around it, close to it, it's the lowest point. Okay, local, max and min. All right, so let's label some things on this graph. So find the points on the interval, closed interval A to B, at which local and absolute extreme values occur. All right, let's go for absolutes first. Pause, label yourself. Okay, this will be an absolute. I know I'm labeling all this, like I'm putting points here. All right, so this would be an absolute max. This is an absolute min. It's too late to be recording. Now I'm making mistakes and I apologize. Okay, do over. Relative min. Relative max. Relative min. I still see something going on there, right? It's labeled, it's got a T. And then I've got this at B. So it's not an absolute, right? So absolutes, we have an absolute max already and we have an absolute min already. Local's definition is that in the vicinity of, right? So we can't say this is a max or a min because there is no right side to it, right? It doesn't have a right side to judge. It doesn't say it goes this way. It doesn't say it automatically goes down. You don't know what's happening on the right side. It's not labeled a local. Locals cannot be endpoints for the purposes of our text, right? Our text. Things like this don't come up on your AP exam purposely because you can argue pretty much anything you want. And some textbooks will take the stance that locals can be endpoints. Our text does not. Locals cannot be on endpoints. Only defined endpoints are eligible, I should say, to be absolute extrema. That's if they fit the bill. This is not the highest point. It's defined. It's defined. It's not the highest though. So it's not anything. Okay. Locals are on the interior only. Okay, and that's by definition of what a local is. Okay. All right, so let's go back to what we're talking about here. So if you can talk about the max, the min, the max, the min, here f prime would be equal to 0. Here f prime would be equal to 0. Here f prime would be equal to 0. But here, when I get to here, f prime is undefined. Undefined. And then if I talk about this right here, your f prime would actually equal 0, but we don't have a local max or a min because basically this is on an entire continuous increase only, right? So it's not changing direction, if you will, like maxes and mins do. You go from increase to decrease, decrease to increase, increase to decrease. You change direction. Here, you're only increasing. Okay. All right. All right. Finding an absolute max or min. All right. So here we go. We're going to apply the EVT to what we know. Here we go. All right. So to find your absolute maxes or mins on an interval, if an absolute max or a min, if an absolute max or a min exists, it exists at an endpoint or at a critical point. We just talked about that. Find critical points. These are candidates for local max or min values. Evaluate the function at the critical points and your endpoints. So this is what we call a candidates test. Okay. So to start, you are always, remember, for EVT to apply, continuous closed interval. Continuous closed interval. Continuous on a closed interval. That's not spelled right. Interval. Okay, which we have. Continuous. Well, polynomials are the best things to use because always continuous. So I will start with my x values and then my label. I'm making like an XY chart for myself. I start by putting my endpoints down no matter what. Occasionally, some of your critical points will turn out to be repeat values of your endpoints. Not a problem. So I have to find the derivative because I need critical points. I need my critical points. So that's where f prime of x is equal to 0 or undefined. So let's get f prime. So f prime is 4x cubed minus 6x squared. It's not going to be undefined. F prime is never undefined. Okay. But where is it equal to 0? Well, let's find out. Lots of factoring going on in this section. 4x minus 6. Why did I factor that way? Ooh. And I like factoring. There we go. How about 2x squared coming up? 2x minus. Oh, it's time to give up. Okay. Let's check that real quick before I move on. I took out 2x squared, 2x minus 3. All right. Okay, zero product property says 2x squared equals 0, 2x minus 3 equals 0. So x is equal to 0, or x is equal to 3 halves. So I'm going to add, these are my critical points. So overall, they are candidates. Okay, so the endpoints are not critical points. You use critical points with the endpoints for test purposes. Now I'm taking all of these and plugging them back into F, and you can pause right now and do that yourself. But I'm just going to write down my values because you're all capable of plugging in. So you should get 32. You should get 0, you should get negative 27 over 16, and you should get 0. We plugged back into the original function, f. And then the last part, 3, select the largest value and smallest value as max and minimum respectively. All right, largest. Okay, largest. I should maybe do this instead. Largest, smallest. Right? So let's write that out. So F has an absolute max of 32 at x equals negative 2, and F has an absolute min of negative 27 over 16 at x equals 3 halves. All right. All right, let's do another one. And again, x to the 2/3 over negative 2 to 3. So x to the 2/3 is continuous. You can plug in negative 2 here. You can plug in 0. You can plug in any number for x. You're good to go. So we're good. It's continuous. It's on a closed interval. We have EVT. That means we'll have an absolute max and min. So let's start our process. So I put my endpoints down. Now I got to get my derivative. Which, when rewritten, is 2 over 3 times cube root of 3. I'm thinking x and I write 3. Sorry, everybody. So the rewrite is important so that you can see what is actually happening. F prime it will not equal 0. Will never equal 0. And F prime is undefined where? Easy enough. At x equals 0. So 0 is the other value. Okay, our critical point. This is my critical point. So now I go ahead and plug the negative 2 back in to my original. So negative 2 to the 2/3 is equal to the cube root of 4. Right, you're squaring negative 2. You're taking the cube root of negative 2 squared, which is the cube root of 4. When I plug in 0, 0 to the 2/3 is 0. And when I plug in 3, 3 to the 2/3 is the cube root of 3 squared, which is cube root of 9. What is the largest? What is the smallest? Okay, smallest, largest. Let's write it out. Okay. Absolute max of cube root of 9 at x equals 3. Absolute min of 0 at x equals 0. Okay. All right, 2 more examples. I would suggest you pause and try them yourself. I will go over them, but pause and try them yourself. We have some product rule here. Okay. Let's stick with what I've been. Maybe since it does say y, I'll do that. Endpoints first. So y prime. I'm doing product rule, remember. So that would mean that it's x times 2 minus x to the 1/2, right? That's what that's equivalent to. So plus x times 1/2 times 2 minus x to the negative 1/2 times negative 1. So if I rewrite that, that would be minus 1 over square root of 2 minus x, and actually take that back. I have x over root 2 minus x. Okay, root 2 minus x, and I forgot the 2. I'm simplifying. Am I good now? I think I am. All right, so clearly I think you can see that you're undefined when x is 2, so that's already a critical point. We don't, an endpoint, so we don't have to obviously put it down again, but we need to figure out if we're equal to 0 anywhere. So let's go ahead and simplify this a little bit. So if we are equal to 0, what's the easiest thing to do? I would say to multiply through by your denominator there. So if I multiply the whole thing by 2 root 2 minus x, I'm still getting 0. And then, you know, if you do 2, this would still have the 2, and then root 2 minus x. Oh, that didn't work out so well. And root 2 minus x is 2 minus x. Okay, minus, so basically I did that, and now I'm doing this. These just cancel, if you will. So, right, when I do this, this would cancel with that. So leaving me with just x. So 4 minus 2x minus x. 4 minus 3x. So x is equal to what? 4/3. I'm pausing now, so I try not to make as many errors. I apologize for that. Okay, critical point, 4/3. Plug in. So when you plug in -2, you should get -4. When you plug in 2, that one's easy, you get 0. All right, 4/3. So it's 4/3 times 2 minus 4/3. So that'd be 4/3. 2 would 6/3 minus 4/3, 2/3. So we have 4/3. I'm just writing in pink. So 4/3 times root 2/3. Okay. So hopefully it's easy to tell largest and smallest, right? Smallest. 4/3 root 2/3, I don't know, it's approximation, but it's got to be larger, right, than 0. Okay. So max of 4/3 root 2/3 at x equals 4/3. And absolute min of -4 at x equals -2. Okay. Last one. A little quotient rule. Okay. Again, pause, and then I'm going to have the answer up. All right, we're back. So go ahead and check your work. But that is going to conclude our video on 4.1. If you have questions on the last one, be sure to maybe ask your teacher about it. The one thing I will point out is that I said y will never be undefined, and that is because if you look at your denominator right here, x squared plus 3 will always be a positive value. There's no way to get, right? -3 plus 3 is the only way to get 0 there. And you're never going to get that when you're squaring whatever value it is for x. So you'll never have that type of critical point. But you have one other critical point at 0, and that only requires me to set the numerator equal to 0 to find that. Okay. Sorry this went on a little bit longer than I had planned, but wanted to make sure you got 4.1 down. Okay. We'll see you in the 4.2 video. Bye-bye.